Greetings. This is the fifth lesson in a series of short lessons on basics of power systems engineering. This lesson covers Thevenin's theorem. Network theory includes several important theorems or laws. We have already seen Kirchhoff's circuit laws in a previous lesson. Two other theorems are Thevenin's theorem and Norton's theorem, named after the people who discovered them. I will describe the Thevenin's theorem along with a few examples in this lesson. Norton's theorem will be covered in the next short lesson. Thevenin's theorem states that any linear electrical network or circuit containing only voltage sources, current sources, and impedances can be replaced at any given terminal AB of the circuit by an equivalent circuit that consists of a voltage source, typically designated as V sub Th, in series connection with an impedance typically designated as Z sub Th. This theorem allows replacing any linear circuit with a single voltage source in series with an impedance. In this lesson, which serves to introduce this theorem, I limit our discussions to resistive circuits. Since we are working with resistive circuits, I will change the notation for Z sub Th from this notation Zth to R sub Th. The application of this theorem to AC impedance circuits is straightforward and will be covered in a future lesson. There are three steps in finding the Thevenin equivalence of any circuit. In the first step, we'll find the open circuit voltage that appears on terminal AB of the original circuit. We'll call this voltage VTH, you see it here, which stands for Thevenin's equivalent voltage. In the second step, we zero out all independent sources in the circuit and calculate the equivalent resistance seen from the terminal AB, and we'll call that equivalent resistance R sub Th, or Thevenin's equivalent resistance. To zero out a voltage source, it is replaced with a short, and to zero out a current source, that source is replaced with an open, and we'll see more about these in the upcoming examples. In the last step of forming the Thevenin equivalent circuit, we'll put the voltage source VTH in series with the resistance that we found as RTH, and that forms our Thevenin equivalent circuit. Let's look at an example. In this example, we are asked to find the Thevenin equivalent of this circuit that can replace it at terminal AB. To find the V sub Th, or Thevenin equivalent voltage, we need to calculate the open circuit voltage between points A and B. To do this, all we have to do is to find the voltage across the 10 ohm resistor. The voltage across the 10 ohm resistor appears without change between points A and B because with AB open, no current flows through the 25 ohm resistor. The current through here will be 0, so all of the voltage drop across the 10 ohm resistor will show up at points A and B, or at terminal AB. And therefore, it's all that's needed is to find the voltage across this resistor. In order to do that, we'll first find the current that goes through this circuit. So, looking at this simple circuit here, we can ignore the 25 ohm resistor because it doesn't participate in our circuit. The circuit is only made up of the 100 volt source, 2 ohm resistor, and 10 ohm resistor in series. We add those and divide the voltage, 100 volts, over the total resistance, 12 ohms, and the answer comes to 8.333 amps. That's the current I going through here. Because none of that current goes through the 25 ohm resistor, all of that current will also flow in the 10 ohm resistor. So the voltage across the 10 ohm resistor, then based on Ohm's law, is the product of the current that goes through it, which is the 8.333 amps, times the resistance itself, which is 10 ohms, and that gives us the voltage across the 10 ohm resistor, which is 83.33. That same voltage obviously appears also between points A and B, 83.33 volts. So we have found V sub TH, the open circuit voltage between points A and B. Now we need to find the R equivalent, and we find that by first zeroing out the voltage source, which means replacing the voltage source with a short circuit, and then looking from the port AB into the circuit and calculating the equivalent resistance seen from there. Here is what the circuit looks like with the voltage source removed and replaced by a short. We can see that our equivalent here is going to be the parallel combination of 10 and 12 added to the 25, because the combination falls in series with the 25 to form the R equivalent. I'll show the calculation on the next slide. So here is the parallel combination of these two, and here is the 25 ohms being added, and the total comes to 26.67. And as mentioned earlier, we'll rename this equivalent resistance to R sub TH, meaning it is our Thevenin equivalent resistance of the circuit. We can now form the Thevenin equivalent circuit by putting this resistance in series with this voltage source, seen on the next slide. Here's the equivalent. Thevenin voltage of 83.33 volts in series with the Thevenin equivalent resistance of 26.67 ohms. And of course, these are the points A and B. Let me just take a short detour and do a little bit of introduction. My name is Fuad Albandi. I'm a PE in electrical engineering. This is the 5th lesson in a series of lessons on basics of electrical power engineering that I have published on the YouTube. You'll find my name and email address on this page. Here they are. You can visit my website at the link given here, own-your-destiny.mylearnworlds.com. I am now going to continue this lesson with example 2. In this example, we are asked to find the current through the 10 ohm resistor, this one, using Thevenin's theorem. To do this, I'll remove the 10 ohm resistor from the circuit, find the Thevenin equivalent of the remaining circuit from here down, and then replace the 10 ohm resistor back into that Thevenin equivalent circuit and find the current from that. First step in finding the Thevenin equivalent circuit is to find the open circuit voltage between points A and B. So we remove the 10 ohm resistor and we'll find the equivalent Thevenin circuit for the remaining circuit. The first step to do that is to find the voltage between points A and B, plus or minus VAB, which we call V sub TH. The next step, of course, is to short this out and find the REQ, and we'll call that RTH, and that's all we need to form the Thevenin equivalent circuit. To find the voltage across A and B, we can first calculate the equivalent resistance that the 120 volt voltage source sees looking into the circuit in this way. You can see that the equivalent resistance involves 4 resistors here, 3 ohm, 5 ohm, 20 ohm, and 25 ohm. And this one does not, the 8 ohm resistor does not come into play. And of course, the 10 ohm resistor was already separated from the rest of the circuit. To find this R, looking into the circuit from this port, we'll see that we first need to add 5 and 25 because they're in series. Remember, we ignored this. So 5 plus 25 is one leg of this parallel combination. The other leg is 20 ohm resistor. So we take the parallel combination of 25 plus 5 and 20. And once we have that, we'll put that in series with the 3 ohm resistor, which means we add 3 ohm to that, and we get 15 ohm for R. Now that we have the equivalent resistance seen by this voltage source, we can find this current by dividing 120 over that resistor, and that was 15 here. You see that on the next page, on this page. So I going through here is 8 amps. I would like to explain something called a current divider. If you have a current such as I coming to a parallel combination of resistors, and let's call them R1 and R2, I is going to get divided in between two currents, I1 and I2, each going through one of these two branches. If you want to calculate, for example, I1 equals I, the overall current, times a fraction with R2 in the numerator and R1 plus R2 in the denominator. What this means is that the current that goes through this branch here is proportional to the resistance of the other branch, this one. So R2 goes in the numerator, R1 plus R2 goes in the denominator. I'll apply this formula to calculate the current I1 that goes through the 5 ohm resistor. Once again, remember that this 8 ohm is not part of our circuit, so we have current of 8 amps coming to this junction, and it's going to be subdivided into an I1 and I2. We don't need the I2, but that would be the current that goes through the 20 ohm resistor. I1 is going through the 30 ohm resistor because these two are in series now, forming a branch with 30 ohm resistance. So the current I1 that goes through the 30 ohm resistor is going to be 8, this current, the main current, times 20, which is the resistance of the other branch, divided by 20 plus 30, 30 being the resistance of this branch. And that comes to 3.2 amps. So I1 going through this combination of 5 and 25 ohm resistors is going to be 3.2 amps. Now that we have current going through the 25 ohm resistor, which is the same as the one going through the 5 ohm. So the current through the 25 ohm resistor is 3.2. If I multiply the two, the current in amps by the resistance in ohms, that will give me the voltage drop across the 25 ohm resistor. And that has come to 80 volts across here. Just like the way I reasoned in the previous example, that same 80 volts shows up between A and B, points A and B, plus or minus 80 volts. So that means that we already have our Thevenin equivalent voltage, which is 80 volts. In our next step, which allows us to find the Thevenin equivalent resistance, is to zero out the voltage source, which again means to replace it with a short, and look from port AB into the circuit to find the equivalent resistance. You can see that starting from the left and going toward the right hand side. You first have a 3 and 20 in parallel. The result is then in series with 5, and then the overall result of those 3 is in parallel with 25, and then 8 gets added to it. I have an equation that has all of those points in it. Remember, we have 3 and 20 in parallel, 5 added to it because it's in series. The overall value that was obtained up to this point is now in parallel with 25, and then after that we'll add the 8 to it because 8 is in series with the rest, and the answer comes to 13.83 ohms. Therefore, that is our RTH. All that's left to do now is to put the RTH in series with the voltage source VTH, which is done on this page. And this is our Thevenin equivalent circuit. To find the current through the 10 ohm resistor, we'll put that resistor back into this circuit between points A and B, and we'll calculate the current going through this circuit, and that simply is, by Ohm's law, is 80 divided by sum of those two resistances, and that current comes to 3.357 is the current that we were looking for through the 10 ohm resistor. Let's do another example before finishing. This next example will contain a current source instead of a voltage source. The circuit in this example contains a 15 amp current source as seen here. The process is the same as the one for example 2. We'll first need to remove the 10 ohm resistor from the circuit and find the voltage across AB. By the way, this is the same circuit as example 2, except that this one has a current source instead of a voltage source. Here is the 10 ohm resistor removed. We have 15 amps of current flowing through the 3 ohm resistor. That 15 amp comes to this junction. The 8 ohm resistor is not part of our circuit for this calculation, so we can use the current divider formula that you've seen before to find the current through the 5 ohm resistor, which is the same current that goes through the 25 ohm resistor. So we have a pair of parallel resistors, a 20 ohm and a 30 ohm, sum of 25 and 5, and the 15 amp current is going to be divided between those two. I'm interested in the current that goes into this branch, calling that I1. You can see that I1 is equal to the total current, which is 15 amps, times 20 ohm divided by 20 plus 30, 30 being this branch, 20 being the resistance of this other branch. And if you do the calculation here, you see that I1 through here is 6 amps. Same current goes through this resistor, again 6 amps. So we can easily find the voltage across the 25 ohm resistor by multiplying 6 amps times 25 ohms. That's done on the next page. VTH is equal to VAB by definition, and that comes to 150 volts. In the next step, I need to zero out the current source, and remember, we zero out the current source by taking it out and leaving an open circuit in its place. Once I've done that, I'll look from the AB port into the circuit to find the R equivalent, or RTH. Here is the current source gone, and here we are looking from AB port into the circuit. The 3 ohm in this case does not come into play. I have a 5 and a 25 in series, 5 and a 20 in series. That comes to 25, and that 25 falls in parallel with another 25, which results in 12.5 for this combination here. And that 12.5 ohms will be in series with the 8 ohm. Let's look at the calculation on the next page. We have 25 in parallel with the other 25 plus 8, and the total comes to 20.5 ohms. That's R equivalent here, which is the same as RTH by definition. Now that we have both VTH and RTH, we can form the Thevenin equivalent circuit. Voltage source of 150 volts that was found in a previous step, in series with the resistance of 20.5 ohms, which was also found on the previous slide for RTH. And we have our 10 ohm resistor still separated from the circuit. To find the current through it, we'll replace that 10 ohm resistor back in the circuit and find the current by dividing 150 volts over the sum of these two resistances. So 150 over 10 plus 20.5, 30.5, gives us the 4.918 amps that goes through the 10 ohm resistor. We are at the end of lesson 5. This is Fuad Al-Bandi, founder of the educational group Own Your Destiny. Please click on the subscribe button and visit my website given on this slide right here. Email me with any questions or suggestions. Thank you for watching this presentation, and I hope to see you in another one of my lessons.